Dear students, this is Kavita BS. In this session, I am going to explain one of the experiment which verifies the Maxwell's law of velocity distribution. This topic is related to BSc course Physics subject, paper 3rd, Thermal Physics, Radiation and Optics 1. And this topic is in the lesson Thermal Physics of Unit 1. Let us start the discussion. So, in the previous session, we have already discussed the Maxwell's law of velocity distribution. In this session, we will discuss the Stern's experiment to verify this Maxwell's velocity distribution equation or law. So, the scientist Stern designed a more precise apparatus to verify the Maxwell's law of velocity distribution. The experimental arrangement consists of the oven with a opening O, where we get the cesium atoms, and this is the slit S, and this represents the tungsten wire. Whole arrangement is placed inside the evacuated chamber. Before conducting the experiment, it is arranged that the opening O of the oven and the slit are along the same horizontal line. Then the experiment is conducted in two different parts, that is, in the absence of gravitational field and in the presence of gravitational field. In the absence of gravitational field, the cesium atoms from the oven will move through the opening O and then through the slit S, then incident at point D on the tungsten wire. They do not undergo any deviation, means they are moving along the straight line, then incident at point D on the tungsten wire. This will happen when the gravitational field is absent. The next part is the experiment is conducted in the presence of gravitational field. In this case, the cesium atoms experiences the parabolic path. Instead of straight line motion, they experiences or they describe the parabolic path. In the experiment, it is observed that the cesium atoms which are moving along the path A will reaches the tungsten wire at the position D1. Similarly, the cesium atoms which are moving along the path B will reaches the position D2 on the tungsten wire. In the experiment, it is also observed that the cesium atoms which are moving along the path A will have greater velocity than the cesium atoms which are moving along the path B. It is also observed that the cesium atoms which are moving along the path C will not reach the tungsten wire. Then, after reaching the tungsten wire, these cesium atoms will undergo ionization and get re-evaporated. These re-evaporated cesium atoms are collected by the negatively charged detecting cylinder which is surrounding the tungsten wire. And this charged detecting wire can be moved to different positions of the wire. Here, the magnitude of the current in the detecting cylinder represents the intensity of cesium atoms at various positions, which means the magnitude of current, ionization current, represents the number of cesium atoms which are incident on a particular position at a particular position on the tungsten wire. And by measuring the velocity in terms of distance from the point D, the vertical distance represents the velocity of the cesium atoms. Then if you plot the graph, that is ionization current versus velocity, we get the graph which is exactly similar that of the Maxwell's velocity distribution curve. So here velocity is nothing but distance from the point D, and ionization current represents number of cesium atoms on the detecting cylinder. So this curve or this graph is exactly similar with the Maxwell's velocity distribution curve. Hence, this result verifies the Maxwell's law of velocity distribution. So these are the books in the previous session. Already I mentioned the textbooks for your reference. Thank you.